Hello, grade nines. Today, we're going to talk about comparing and ordering rational numbers. So far we learned what a rational number is. A rational number is any number that can be represented as a fraction. But just because it's rational doesn't mean it's always in fraction form, but fractions can be really helpful to kind of help compare and order with. Now we're going to talk about different strategies on how we can compare and order different rational numbers in terms of sizes. Now, so far, you have skills from previous years in how you can compare two numbers. Those skills still exist, okay? So things that I just want to point out so that you can always refer back to, even though they're not part of the lesson, things that you would have known by now. Positive numbers, always bigger than negative numbers. Doesn't matter what they are, positives will always be bigger than negatives, okay? Other things that you know is how to compare decimals, right? If I said 1.8 versus 2.7, which one's bigger? You would tell me 2.7. If I said 0.7 repeating versus 0.75, which one's bigger? Hopefully you tell me 0.7 repeating. Okay? Now those skills that we've had and we've used to compare rational numbers before still apply. We're just going to be talking more specifically today on different strategies to compare rational numbers when they're in fraction form. Now, of course, if you get two fractions and you can easily convert them into decimals, like that can always work. That can always be your strategy. So if you get like 7/99 and, 5/8, and you're like, oh yeah, I can convert both of those into decimals pretty easy and I'm good and confident at comparing decimals to each other, awesome. All the power to you. But today I'm just going to remind you of those strategies of how to compare things when they're in fraction form. So, strategy number 1 is fractions with the same denominator. Whether we've made them into common denominators or they already came in common denominator form, when I have the same denominator, the larger fraction will be the one with the larger numerator. So larger fraction will be the one with the larger numerator. And this should be fairly straightforward, but if I'm taking a look at the examples, 5/8 versus 4/8, I can even show you pictorially. So these circles I'm going to break up into 8 even-sized pieces. The key thing is if I'm ever drawing pictures to compare things, my pictures have to be good pictures. Because if I split my pie, my pizza, whatever you want to think of this circle, into 8 slices, but all 8 slices are like drastically different from each other, and I shade whatever amount I need to, so 5 for one of these and 4 for the others, it might make it really hard to tell which one's bigger and which one's smaller. So I do want to make sure all of my pieces are of even size. So here's 5/8, here's 4/8. And did I need to draw the picture for this? No. But can pictures sometimes be helpful? Yeah, totally. So I know that 5/8 is the larger fraction because it has the bigger slices of pie. Okay? It also has the larger numerator when the denominators are the same. Now sometimes common denominators we can easily convert to, no problem, and it's pretty easy to do so. But sometimes it's actually easier to have the same numerators instead. So instead of having the same denominators, let's talk about fractions with the same numerator. So the fractions with the same numerator, the larger fraction will be the one with the smaller denominator. And as we talk about drawing these pictures, hopefully it becomes clear as to how you know that. Remember when we're talking about these fractions, the denominator tells me how many times I've cut up a whole. Okay, so my whole pizza or my whole cake or my whole pie, whatever you want to call it, is split up into 8 pieces. And I have 6 of those pieces. 1, 2, 3, 4, 5, 6. My next pizza or pie or cake or whatever you want to call it is split up into 12 pieces. So, and again, we want to make sure we're drawing this as best as possible. And you'll notice that when I'm drawing it, I erase some of my lines because they weren't great. And it's okay not to be perfect the first time. The idea is just don't stick with it if you know it doesn't look good. Okay? So here's my pie now split it into 12 pieces. And if I have 6 of them, well, that's actually only half, which based on my shaded region, I can tell is the smaller version. So 6/8 is the larger one. Now, again, you might be like, Miss T, I could have just reduced both of those fractions, and then I could have told you that 3/4 was bigger than 1/2. Yes, I know, okay? But we're trying to do examples that are easy to draw, but also so that we can understand the concept behind it, right? If I have like one chocolate bar even, and if I'm splitting it with like 3 people, versus if I have a chocolate bar and I'm splitting it between 30 people, if I have one like piece out of each of those chocolate bars, the one split up 3 ways or the one split up 30 ways, the less divisions I've had to make, the bigger my piece is. So my first chocolate bar where I only split it up into 3 pieces, my piece is actually still pretty big. But if I have a chocolate bar and I split it up with 30 people, I have to share with 30 people, I might not even get even a worthy size piece of that chocolate. It might be like half of a nibble, okay? So if I have fractions with the same numerator, whichever has a smaller denominator will end up being the bigger fraction. And that's why, because it's all about the sizes of the pieces. Now, when I take a look at 2 fractions, I might be like, yeah, I can make them into equivalent fractions. Not equivalent fractions. I can make equivalent fractions that have the same numerator, or I can make them into equivalent fractions that have the same denominator and use either of these first 2 strategies. But sometimes I get these fractions like these. And quite honestly, this would be a pain in the butt to make the numerators or the denominators equivalent to each other. Because if I wanted to make the numerators equivalent to each other, the fraction on the left, I'd have to multiply the top and bottom by 16. And the fraction on the right, I'd have to multiply top and bottom by 15. And yeah, I could do it. I don't want to. If I wanted to make common denominators, I'd have to do, again, something similar. Probably have to multiply top and bottom of the left one by 27 and the top and bottom of the right one by 32. And no one wants to do that. Now, the goal here in grade 9 is not just to get the final answer. That's part of it. But the goal is also to understand strategies to allow us to do things more efficiently. So even though I could do some of the strategies above, there's actually a better strategy for this situation. And that's to compare both of those fractions to a half. Now, I'm going to look at each of these fractions one at a time. So let's look at this one here. 32 is the denominator. So again, ignore the numerator right now. Just think of the denominator 32. I want to think of what over 32 would be an equivalent fraction to 1/2. And that would be 16 over 32. Because I have 15 over 32 instead of 16 over 32, what that tells me is this fraction, whatever it is less than 1/2. It's less than 0.5. probably pretty close because 15 is pretty close to 16. But I know it's going to be less than 0.5. So it'll be 0.4 something perhaps, but definitely less than 0.5. Now let's take a look at this other fraction here, okay? And think about the same denominator, 27, not changing the denominator, but what would be half of 27? Well, that would be 13.5 or 13.5, however you want to write it. Now 16 is bigger than 13.5, which means 16 over 27 is greater than a half. And notice in this example, oops, I didn't want to erase that. I just wanted to erase this guy. Notice in this example, we are taking a look at both of these two fractions and just thinking, is this fraction like less than a half or more than a half? Now, if they happen to be one's smaller than a half and one's bigger than a half, or one's equal to a half and one's smaller, or something like that, where there are like different answers, I can really easily tell which one's bigger. It's the second fraction here. Because if the second fraction is greater than a half, and the first fraction is less than a half, then that second fraction is going to be the larger of the two. Now, this method doesn't always work the way we want it to, but is usually my first strategy if I don't look at the fractions provided to me and immediately know what they are in decimals, or could immediately convert them to decimals. So like 15 over 32 and 16 over 27, like those aren't fractions that I'm converting by mental math into decimal. So that's where I'm kind of comparing to this half piece. Now, if I look at the next example, I'm going to try and do the same thing and look at this fraction. So this one has a denominator of 58. Half of 58 is, so half of 50 is 25. Half of 8 is 4. 25 plus 4 gives me 29. So 30 over 58 is just over a half, right? It's greater than 1/2. Not by a ton, but greater than a half. If I look at this guy here, my denominator 30, 15 is half of 30, which also tells me that this fraction is just greater than 1/2. Well, that's not really helpful, right? Both fractions are like just bigger than 1/2. So not always the most helpful, but I would say for fractions that I can't convert to decimal really easily, that's my first strategy, okay? I would rather do this than common denominators or common numerators, because look at those numbers, that seems like it's going to be a pain in the butt. If you're like Miss T, I love long division. If I wanted to compare these, I would just do long division for both of these and keep on going until I see a part of my decimal that's different. And I'd be like, cool, all the power to you. That's a great way to go with it. Not always the fastest. So this would be like my go-to strategy of trying to compare two fractions that are kind of challenging fractions. Okay. The next strategy would be visualize the size of the pieces. So I'm going to backtrack and then come back here for just a moment. Remember when we did this question? I mean, you should have. It was like a few seconds ago. But this one here, I had 6/8 versus 6/12. Okay? Let's just talk about the size of the pieces. So let's say this is a cookie, a calf cookie. The circle is a calf cookie. And in the first cookie, I'm sharing it with 8 friends. In the second cookie, I'm sharing it with 12 friends. Which piece will be the bigger piece that I get if I get one of those pieces? Hopefully you're thinking to yourself, or maybe you shouted at the computer screen, and if you did, good for you. But hopefully you look at this and you go, oh, you'll get a bigger piece when you share with less people, right? The fewer people you share with, the bigger piece you get for yourself. Okay, I want you to think of that as we talk about this. I want to talk about visualizing the size of the pieces. Remember, when I have a smaller denominator, the pieces are bigger. If I have a larger denominator, my pieces are smaller. This strategy works when you either have the same number of pieces, so like a common numerator, or you're missing the same number of pieces. So it doesn't actually look like a common numerator necessarily, but you have this same amount missing. So let's talk about the first one when we have the same number of pieces. But I guess we should fill in the blank first. Okay, note, the fraction with a larger denominator will have smaller pieces, right? The more people you share with, the smaller the piece you get for yourself. Okay, if I take a look at this, the first example, I'm comparing 1/15 to 1/18. I want to circle the bigger one. Now, in each of these scenarios, I get one of those pieces, right? I split it up 15 ways for the first cookie. I split up it 18 ways for the second cookie. But in each of these, I get one piece, the same amount of pieces. When will I get more? I will get more when I share with fewer people, when the denominator is smaller. So this here is going to be the larger fraction because I have one of the bigger pieces. Larger denominator means smaller pieces. Now in the next example we're still talking about the size of the pieces, but this one's different. And hopefully you're looking at this and going, okay, this one's different from the question above because in the question above, the numerators are the same. But in this question, the numerators are different. Why can I use the comparing of the pieces strategy? Because both of these, I am almost full. I almost have the whole entire thing. I'm just missing 2 of those chunks. So if I split up a cookie 25 ways and I got 23 of those pieces, that means I'm missing 2 of those pieces. 2 of those pieces go elsewhere. I don't have them. And in this fraction here, I take a cookie, I split it up 31 ways, I get 29 of those pieces. I'm again missing 2 of those pieces. So in this case, we're visualizing the size of the fraction, or the pieces of the fraction, because I'm missing the same number of pieces from each one. So I'm just going to write kind of in the side here, both are missing 2 pieces of the whole, right? Because 25 minus 2 is 23, and 31 minus 2 is 29. That's why I can use this strategy of comparing pieces here in this example. Now let's talk about which fraction has smaller pieces. And if you remember, the fraction with the larger denominator will have smaller pieces. So this fraction here has smaller pieces. Okay? Now remember, I am missing pieces. I'm missing specifically 2 pieces. Here I'm missing 2 smaller pieces. Here I would be missing 2 larger pieces, which makes this the larger fraction. Now, these denominators are actually pretty hard to draw, so I'm going to do an example of this, pretty much the same concept, off to the side here. So let's talk about 3 out of 4. I'm missing 1 of the pieces. And 5/6. Again, missing 1 of the pieces. And let's visualize it. I actually want a perfect circle. Or at least close. It's pretty good though. Okay. Oh. Okay, here are my 2 cookies. The first one I'm going to split up 4 ways. Again, trying my best to make these pieces look equal in size, because if they're drastically different, that'll be very confusing. And then I'm going to draw 5 out of 6. One, 2, 3, 4, 5. In my 2 pictures, where do I have more? I have more in this guy, because this is the one with smaller pieces. And in this case, I am missing a smaller piece. This chunk is what I'm missing. This chunk is what I'm missing, because I'm missing a smaller piece that ends up being my bigger fraction. Now, you're welcome to draw that, but when I get to these like fractions where my denominators are quite large, it's going to be a real big pain in the butt to draw. So I wouldn't recommend drawing as your go-to, but if I'm using smaller fractions, or I want to see how that looks like in smaller fractions, then it's more acceptable to draw, because it's easier to do. Hopefully that made sense. Okay. In the next one, so we're talking about if they don't have a common denominator already, can we turn them into a common denominator? Or can we turn them into a numerator and kind of go on? Yes, of course we can. So here, we don't have a common denominator. We don't have a common numerator. Remember that both of these are negative now, right? Look, this is a negative fraction and this is a negative fraction. So when I'm looking at a number line, I want to talk about what's further to the right is my bigger number. I also want to talk about like the size of negative numbers, right? -5 is smaller than -2 because it's further to the left. It's further into the negative land. Okay, so just something to kind of keep in mind when we're comparing these fractions. So these negative fractions that I have here, I am going to make them into common denominators. And if you're looking at these, the common denominator that I'm going to make is for both of these to have a denominator of 28. So I'm going to keep the negative up at the top for both of these, just so that they're in the same place, because sometimes just when fractions look different, it can make us confused. But we have the choice of where to put that negative, either out in front or with the numerator. I like to have it with the numerator because I find that that's less confusing for me. If you like them both out front, great, all the power to you. Now, I want to take a look at which one of these fractions is larger. And now that I have a common denominator, I'm just simply comparing the numerators. And remember, because I have negative numbers, -20 is actually bigger than -21. It's further to the right on the number line. So making sure that I'm respecting the negatives that are there so I can continue this. Okay. And the last little strategy here is just going ahead and converting these to decimals. So when I take a look at this next example, we learned in section 1.1 all about converting fractions to decimals. These fractions, hopefully you look at and you're like, oh yeah, I know what those are. Take a moment, write down what they are. What's 3/4? It's 0.75. And what's 7/9? It's 0.7 repeating. And I can go ahead and compare these. Now, I know that 0.7 repeating is bigger than 0.75. And if you're like, what? But 75 is bigger than 7. That's not how comparing decimals work. Remember, 0.7 repeating is just like this forever. It still repeats, even though I stopped, but it still repeats. And when I'm comparing to decimals, I'm comparing one place value at a time. So the first place value was identical. the second place value, oh, 7's bigger than 5. So 7/9 will be the larger fraction. Okay, so lots of strategies. Common denominators, common numerators, comparing to a half, the size of the pieces, converting to decimals. All different things you can do. I will never tell you to use one strategy over another. I will always just say, do what makes sense to you. So we have a couple of examples here, and we are going to take a look at each of them. Okay. So the first one to talk about is the one here that says 5/9 versus 6/13. Okay. Now, if I'm looking at those fractions, just so that you kind of know what thought goes through my head, just in case you're curious, my first thought is always to convert to decimals, but only if I can convert both of them to decimals. Yes, 5/9 I could do it, feel super great about it. 6/13, not so much. If I can't convert to decimals, then I move on to the second strategy. And my second strategy is comparing to a half. Now, 5/9 is more than a half, because half of 9 is 4.5. So 5 is larger than a half of 9, which means 5/9 is larger than a half. 6/13 is under a half, because half of 13 is 6.5. So when I take a look at this, the larger fraction will be 5/9. So this is more than half, and this one is less than half. And if you took a different strategy, maybe you were making common denominators or making common numerators, like great, all the power to you. But you might have noticed, oh man, that took some time to do. This strategy was a little bit faster. So it's not about necessarily getting the correct answer. It's about getting the correct answer and being efficient in your ability to get that correct answer. B. So I'm looking at this and going, okay, I don't know how to convert fractions to decimals with denominators of 19 or denominators of 17. I'm not converting these to decimals. Next, I'm looking at this and being like, okay, these are both clearly bigger than a half. That's the next strategy I thought about in my head. The third thing I'm thinking is, hey, the numerator is for each fraction is 1 smaller than the denominator. So I'm thinking about, hey, each of these fractions is missing one of those two pieces. Now, the bigger fraction will be the one that's missing less. And because the larger denominator tells me that I will have smaller pieces, if I have 18 out of 19 pieces, that means I'm missing only one small piece versus 16 out of 17 where I'm missing one larger piece. So 18 out of 19 will in fact be the larger fraction. Again, faster than making common denominators, faster than making common numerators. Just another strategy to help us do things efficiently. Next one. Again, these aren't fractions that I'm confident converting into into decimal form. If I'm taking a look at these, both of these are less than a half. And for both of these, I either have or am missing different numbers of pieces. So those strategies, those won't work. So my next thing is making either a common denominator or a common numerator. Now, probably in previous grades, you've been used to making common denominators every single time. But looking at my numbers, it's actually easier for me to make a common numerator, right? If I make a common numerator, I just have to multiply top and bottom by 5 for the first fraction and top and bottom by 2 for the second fraction. So I get 10 over 35 versus 10 over 34. Way easier than me multiplying the left one top and bottom by 17 and the right one top and bottom by 17. Okay? And when I do common numerators, again, I have the equal amount of pieces of each one, but the larger denominator will have smaller pieces. So I have 10 small pieces in the first one and 10 larger pieces in the second one. which tells me the second fraction is going to be the larger of the two. Last but not least, I immediately look at this and think common numerators, which is great. But I'm also immediately looking at this and being like, uh-oh, there's negatives. Okay, and when we take a look at negatives and we're comparing and ordering negatives, it's essentially the opposite of things were positive, right? 10 is bigger than 5, but negative 10 is smaller than negative 5. So it's the opposite kind of order if those were flipped from both being positive to both being negative. So sometimes when I'm dealing with negative fractions, I actually start by pretending they're both positive, figure out my answer, and then swap it, if that makes any sense. And so that can be something you can do. So I am going to start by pretending that both of these fractions are positive because it's easier for my head to visualize positive pieces of pie. And if I'm taking a look at this, the larger the denominator, the smaller the pieces. Which means if I have 13 small pieces as opposed to 13 big pieces, if these were positive, this would be the larger fraction, but they're not. And because they're not positive, the opposite answer is true. The second fraction will be the larger one because I have 13 negative smaller pieces, which is greater than 13 negative larger pieces because negatives order is the opposite to positives order. Okay, the last two examples we have is we're going to be placing these numbers in order, these rational numbers in order. And when I give you rational numbers, kind of like in these two examples, they can be written in different forms. They can be written as decimals, they can be written as fractions. You can have a combination of them both. Okay? One thing I'll point out, I kind of skipped over it at the top here, but this is language that you are expected to know. So ascending means to go from smallest to largest, and descending means to go from largest to smallest. And in my head, when I think about ascending and descending, like, you might not see those words used a lot outside of math, except I always think that in math, they're like, oh, he descended into hell, and then ascended into heaven. Ascended is up, and descended is down. So I think of ascending as going from smallest to greatest because it's going up in value. Descending is largest to smallest because it's going down in value. I know up doesn't start with an A, but like it sounds similar, you know? You got to work with me a little bit here. So we're going to take a look at these two examples. The first one we're going to do, we're just going to place these on a number line. Now, when I take a look at this, my number line isn't labeled other than the number 0. So I want to start by labeling my number line. I'm going to go up by ones because when I'm looking at these numbers here, some of them, like I could see the number 2 and negative 3 and something, negative 2.25, right? So they're definitely going to be further away from 0. So I want to make sure I have space for that. Now, when I take a look at these, hopefully you're like, okay, the decimals I'm going to keep as decimals because I have an idea of where they go. Can you take a moment and plot the numbers or the rational numbers that you feel confident with? Just for this example. We'll pause the video, give it a go. And welcome back. Okay. Hopefully you looked at this and you're like, okay, I feel confident that 2 goes here. Okay. There's probably more that you feel confident about, but hopefully you all plotted the number 2. Now, as I go through these, I'm going to plot, I think the decimals first because I feel like decimals are easier to plot. But kind of up to you where you want to go with it. So I'm going to just skip 4/5 temporarily. I'm going to look at this guy. So negative 2.25. that's like -2 1/4. And so that's looking in and around there. -2.25. Because between -2 and -3. And 0.25 is 1/4. It's one of my sight fractions. So I split that jump into 4 chunks, right? 1, 2, 3, 4. And then counted one of those chunks. 0.45 repeating. That's definitely under a half, but really close to a half. Okay, so taking a look, half exists at the halfway point between, not 1 and 2, but 0 and 1. So 0.45 is going to be really close. 0.45 repeating. It's going to be really close to that halfway mark. -0.1, or I could think of it as -10, 1/10. Okay. I can, if I want to, split this up into 10 pieces. And do my best for it. If you're looking at this and thinking, oh, Miss Thibodeau, that's not perfect. You're right, it isn't perfect, but it's pretty close. So this here, angle that arrow there a little bit. You get -0.1. Now, the other guys, these ones, these fractions. Hopefully you're looking at this and thinking, Miss T, this is so nice of you. These fractions are so easy to convert to decimals. I feel really confident with them. And if that's the case, awesome. All the power to you. If you want to draw them as fractions as well, though, that's also super cool. So I can either think of 4/5 as 0.8, right? Because 4/5 is the same as 8/10, which is 0.8. Which I can approximate and be like, yeah, it's in and around here. But whenever I'm labeling something, I want to label it in the form it was originally given to me in. So since it was written as 4/5, even though I thought of it as 0.8, I want to label it as 4/5. Because that's like me saying, hey, call me Miss Thibodeau, and then you being like, I'm not going to do that. I'm going to call you Jellyfish instead. Right? You can't just change the name or a way that something is being called. You need to make sure that you name it as it's requested to be named. Okay? So if it's called 4/5, you got to call it 4/5. The last one is -3 1/3. And you could think of that as -3.3 repeating, because 1/3 is one of our sight fractions. But I could also think about that as just splitting the jumps into 3 and then taking one jump. So I get -3 1/3. Again, I should be labeling it in fraction form because it was given to me in fraction form. This is one way, the use of a number line is one way to help us order numbers. It's a nice visual place for us to put these values. You don't have to use a number line, but can be helpful. Now, more often than not, if I'm giving you order or irrational numbers to order, I will just give you a list of these. Okay? And when I take a look at these, and I'm not putting them on the number line, yes, I can draw a number line. That's a strategy I can have. But I'm trying to order them. The first thing I do is I look for the positives and the negatives, and I separate them. We know that negatives are always going to be smaller than positives. So those two yellow highlighted values will for sure be smaller. And since I'm putting them in ascending order, I'm going to put the smallest one first. Now, if I'm looking at those two yellow ones, I've got -3 and -1 point something. -1 7/8. Now, I don't actually have to do any conversions for me to know the order of them, because I automatically know that -3 is less than -1 7/8. Just because that whole number component, that 3 is a different value than 1, says small, that -3 is a smaller integer than -1. So the decimal value doesn't make a difference here. All right. The next thing I have are these blue ones. And I know the blue ones are coming next because the yellow ones are all gone. Pew, pew. Now I could think about converting them into decimals. I can't really convert 2/7. But I could convert 1/2 to 0.5. It's one of my sight fractions. So I know that this guy's 0.5 will be less than 0.6 repeating because that's how the decimal ordering works. But 2/7 isn't one of those fractions that I can easily convert into a decimal. But the nice thing is 2/7 is definitely less than 1/2, right? It is smaller than 1/2 of 7. 2 is smaller than 1/2 of 7. So since this guy is less than 1/2, this guy's equal to 1/2, and this guy's larger than 1/2, I can go ahead and complete the order. Again, writing it in the form it was given to me in. I can't just change the name because I want to. But look how little amount of work I had to do to get that order right, because we can use the various strategies we talked about in today's lesson to help us get that order set. Okay, that's it. There's some practice that follows. If you can please work on that, that would be fantastic. Otherwise, that is it. That is all. I hope you have a really great day, and I hope to see you soon. Bye.